Hi, it's Kiffin Bates here, and today I want to talk about Aleph Zero because I mentioned it in a post I made a couple of days ago listing the 17 mathematical equations that meant a lot to me, and Steve Tendon suggested that I actually explain what that symbol means because quite a few people got confused when they saw it. So the symbol relates to mathematics, and in particular to the mathematics of infinity, because a German chap called Georg Cantor came up with a way for us to get our heads around what actually is going on in the world of infinity. And the funny thing about the mathematics of infinity is that it's actually founded on a concept that we all understood intuitively as kids and then lost when we learnt more about counting. And as adults, what we do when we want to know how many of a particular object there are in a room, say you're trying to count chairs, we recite a little nursery rhyme. We go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 chairs. And we've lost touch with what we're actually doing there. Whereas when we were 5 or 6 year olds in the playground with bags of marbles, we used the principle that is actually the basis of understanding infinity, strangely enough. So I'll give you an example. I'm a kid, I have a bag of blue marbles, my friend has a bag of red marbles, and we want to know who has more marbles. And when you're that age, you don't count. What you do is you pair. You each take one marble out and put it next to your friend's, and you keep doing that, and eventually one of three things happens. Either you run out of marbles, which means that you have less, or your friend runs out of marbles, which means he has less, or you both run out of marbles at the same time, which means you have exactly the same number. And it's that third case that Georg Cantor then took and extended to the infinite. He said, let's define the size of the counting numbers, which just keep going on and on and on and on, with a symbol. We'll call it Aleph Zero. And then, and this is the clever part, he said, if you can find a mechanical way of pairing the counting numbers with the set that you're looking at so that every counting number has an element in the other set that it corresponds to and vice versa, then those two sets are defined as having the same size, Aleph Zero, the countable infinite size. And it turns out that there are some fairly counterintuitive properties that pop out when you do that. So, for example, the counting numbers and the even numbers have the same size because the pairing method is that you double the counting number in order to get the even number that it corresponds with. So 1 corresponds with 2, 2 corresponds with 4, 3 corresponds with 6, and so on and so forth. Now, of course, because there are an infinite number of counting numbers, it never stops, but you can see that that mechanical method of pairing the two means that for every counting number there is an even number, and for every even number there's a corresponding counting number, and therefore by this pairing rule they have the same infinite size, Aleph Zero. And it turns out that actually fractions are the same. You would think there must be a lot more fractions than there are counting numbers, in the same way that you would think there are half as many even numbers as there are numbers, counting numbers. But if you say the size of these two sets is the same because you compare them, it turns out there is a mechanical way of pairing fractions with counting numbers so that for every counting number you cover a fraction, and for every fraction there's a corresponding counting number, just like pairing the marbles. So that's the basis of Cantor's theory of the infinite, I suppose, and it really does boil down to the way that we used to compare things when we were kids, just extended to the uncountable. Anyway, hope you found that interesting. See you in the next video soon. Bye for now.